Greetings, AP Chemistry students. Today we're going to talk about solubility, and then we're going to get into a little bit of spectroscopy as well. So there's the like dissolves like principle with solubility. It says that substances with similar intermolecular attractions tend to be miscible or soluble in one another, and substances with different ones obviously are not. Miscible just means that it's soluble in any concentration. So, for instance, you may be familiar with, like, sugar will dissolve in water, but not very well, and there's a limit to how much sugar you can dissolve in water. On the other hand, something like ethanol and water can be mixed in any proportion. Right? So that's what miscible means. Don't worry too much about that term. It basically just means soluble. Now, polar molecules are more attracted to each other, and they exclude nonpolar molecules because the dipole-dipole forces are stronger than the dipole-induced dipole forces. Now, that doesn't mean that nonpolar things can't dissolve at all into polar substances, but their solubility is going to be quite limited. And that's why, for instance, in this mixture of oil and water, that's why the water is down here on the bottom. It's more dense, and the oil's up here on the top, and they don't mix. If I try to mix them together, it will quickly get separated back out as the water starts to hydrogen bond with itself, and it basically squeezes the oil back out of the mixture. Now, there are some factors that affect the solubility of substances, and that would be the structure of the molecules, for instance, polarity, the ionic charge, and size. The lower the charge and the larger the ions, the more soluble they are. Because in order for an ionic compound to dissolve, like for instance, potassium nitrate, water molecules have to be able to form ion dipole attractions with the ions and pull them apart. On the other hand, if you get to something like, say, calcium sulfate here, the ion dipole forces are not strong enough to overcome the ionic bonds between the positively charged calciums and the negatively charged sulfates. And so this does not dissolve. Once you get up to something like aluminum and hydroxide, that becomes pretty much insoluble because it becomes difficult to separate them. Now, some things that are always soluble are substances in group 1, like sodium and potassium, rubidium, cesium, francium, and lithium, because they are very large ions that are only positive 1 charged. Nitrate is always soluble, and acetate, the C2H3O2. Those things are always soluble because they're quite large and either only have a +1 or -1 charge. So this goes back to Coulomb's law. And in order for a water molecule to come in and form those, like this represents a water molecule, for it to come in and form those ion dipole interactions, it has to be able to first pull the ions apart from each other. Another factor that affects solubility is pressure. And there's this thing called Henry's Law. You don't need to know it's Henry's Law. You also should have seen it in the video the other day. But it says that concentration of gases increases directly with pressure. It does not apply to gases that react with the solvents. But this one, that's why, for instance, one of the reasons or one of the ways to keep a soda from going flat is to keep it under high pressure, to keep the lid screwed on. If you're going to be drinking a can of soda later, don't open it now because it's going to go flat more quickly as the carbon dioxide reaches an equilibrium with atmospheric pressure. And then temperature. Now, the solubility of solids usually increases with temperature, but not always. For instance, if you're trying to make sweet tea, you need to heat up the water and dissolve the sugar into it while it's hot, because it's more soluble in hot water than cold water. And then once you cool it down, it'll actually stay dissolved in what's called a supersaturated solution. And then gas solubility goes the other way. It always decreases with temperature. Gases are much less soluble at higher temperatures. That's why if you want to keep a soda from going flat, the other thing you need to do is keep it cold or refrigerated. A room temperature soda or a hot soda will go flat very quickly compared to a cold soda. This also creates problems with what's called thermal pollution from industrial plants that try to cool off their manufacturing processes, or a power plant. If they dump that hot water directly into a river or stream, that water is going to be at a very high temperature and have less oxygen dissolved in it. And so that can cause the death of fish and other things that live in the water, because there's insufficient oxygen for them to survive. So that's why oftentimes they'll have to cool that water back down and aerate it before they're allowed to dump it back in the water. So this kind of shows Henry's law right here. You can see that as the pressure increases, it pushes more gas particles into the solution, so you have fewer gas particles above it. And then this shows the solubility of several solids as a function of temperature. You can see, for instance, sugar, its solubility goes up quite high with temperature. Same with potassium nitrate. Some other substances, sodium chloride, it's not on this chart right here, but its solubility stays almost completely flat. It's very little effect by temperature. Gases, however, they all decrease quite sharply with temperature. Helium stays fairly flat because it's just really not soluble at all, hardly. But none of these substances are super soluble in water. They're all nonpolar substances. The only way they could dissolve is through some dipole-induced dipole interactions or some dispersion interactions that are all relatively weak compared to water's hydrogen bonds with itself. All right. Now we're going to take a shift into something different that'll start the last topic in this unit, because we're going to be having a test by the end of this week, hopefully. That's electromagnetic radiation is a form of energy that travels in waves. So this is a typical wave. You're probably familiar with the thing on top is called the crest. The low point is called the trough. Its height above its rest position is called the amplitude. But the thing that really matters is that the distance between equal points on successive waves is called a wavelength. So that's the size of the wave, if you will. We'll talk more about that tomorrow. But spectroscopy is the use of electromagnetic radiation to study a substance. Now, we've already studied photoelectron spectroscopy and mass spectroscopy are two things we've already studied. We're going to look at a few more. So microwave spectroscopy is useful for measuring molecular rotation. For instance, if we go back to a water molecule, this polar thing, what happens with it is if you use the right frequency of microwave in a microwave oven, you can actually cause these water molecules to start spinning inside of your food, which generates heat and friction, and that's what actually cooks your food. Is because the wavelengths, if you get the right wavelength of microwave radiation, it lines up with the size of a water molecule and can cause it to actually start spinning. So you can use microwave spectroscopy to essentially measure the size of a molecule. The key term that you're expected to know for the AP exam is microwaves. Go with the rotation of a molecule. Then if we get to smaller wavelengths, infrared is useful for measuring molecular vibrations, which can tell you the difference between single, double, and triple bonds. Because if you use a wavelength that is the size of a bond in a molecule, it can cause that molecule to start vibrating back and forth as it absorbs that infrared light. So if you have a triple bond versus a single bond, you can see these have different lengths, and so they would absorb different wavelengths of infrared. So you could use that to measure bond lengths. That gives us the support for delocalized pi bonding in molecules with resonance structures, that it's not a single bond here and a double bond there. They measure that using infrared spectroscopy. And then we have visible and ultraviolet is useful for detecting transitions in electron energy levels, like from the flame test, where it causes electrons to jump into higher energy levels and then fall back down, and they release visible light or ultraviolet light, occasionally some infrared as well, but mostly visible and UV. And then the last type of spectroscopy that we will discuss in great detail tomorrow, and you've done an experiment with it already, is absorption spectroscopy. Can determine the concentration or molarity of a solution according to the Beer-Lambert law. And we will talk much more about that